So when we're doing exponent problems, we can just use this exponent rules where we can just add the exponents together when we're multiplying here. So we can go 2 minus 5 plus 7. But it's really important to understand and recognize that that minus really means divide. So I could rewrite this as, well, I have x squared x7, that's multiplying by x 9 times. Okay, so I'm using the multiplier x 9 times, and x to the negative 5 means I'm dividing by that same multiplier 5 times. Well, times and divide undo each other, so we have 5 divides canceling out 5 multiplications, and we have 4 extra multiplies. Okay, and we can do it that way as well. So same thing here. We know that we have connected by multiplication. The bases are the same, so I'm going to count that base the same. So it's going to be a to the power 9. Okay, we have a squared in the denominator, meaning we're dividing by a twice. So multiplying by a 9 times, dividing by a twice, means we have multiplying by a 7 times. Here, we've got lots of stuff going on. So I don't really know how to deal with this, other than if I'm ever stuck, I can always just expand. Okay, so I have AB cubed twice. That's going to mean I have A cubed B4 3 times. So that's my multiplier, A cubed B4. I have that 3 times. That's all connected by multiplication, so I can just count up how many A's I have multiplied. 1, 2, and I have 3 here, so that gives me 5, 8, 11. So I have A to the power 11. I have B cubed, B4, 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 all connected with multiplication, all the same base, all connected by multiplication, so I can just add up those exponents. So B, this is going to be 4, 8, 12, 15, 18, so I end up with B to the power 18. Okay, here we just have to keep track of our negatives here, and remember that those negatives here do not have nothing to do with the negative powers. The negative powers are to do with division. So when I work this out here, I can expand this out if I want, but because of the way this works, because I can distribute multiplication across addition, which is 1 power less, I can actually distribute exponents across multiplication. So this really can represent negative 2 to the power 3. This could represent x squared to the power 3. Power to power, I'm going to group count or multiply. Power 6. The negative 2, I could just say, well, xy, that really just means divide by xy twice. Okay, and then I have x, I'm dividing by in the denominator twice, but I do that in 2 groups, so I can do 2 groups of negative 4, and I can do 2 groups of y. Okay, now if I want, I can move that into the numerator, okay, which is what I think I'll do. I'm going to put that power divide, so this is divide, but divide in the denominator really means multiply. So when I work this out, I get negative 2 times negative 2 times negative 2, x to the power 6, x to the power 4. Here I get x squared, and y squared here. And then I can just count this all up. I've got 10 x's in multiplication, 2 x's as divide, so I'm going to end up with 8 x's as multiplication, and I have 4 y's in the denominator as divide. So there we go. Here we just have this doing the same thing, but we are doing this with variables. So we have to be very careful. We're not going to distribute like this because we can't distribute. That's going to be group counting or multiplying here. So we're not going to distribute that to those 2 terms. We're just going to do x to the power 3 groups of 2a gives me 6a. Okay, this is just y squared. I've got two groups of x to the 2a, so x, we don't know what a is, but we know we're going to do it twice as many times as we have listed here, so we're going to do that 4a times. Okay, and now we can say, again, we don't know what a is, but we know we're counting it 6a times, and we're dividing it 4a times. Well, we've got an extra 2a in the multiplication. Here we have an extra 4y's in the division. Okay. So here, these are just equivalents. How can we show their equivalence? Well, we can just use some multiplication. We could just put an equal here, and I can just start getting these negative powers. Now I can use those negative powers in there, or what I could do is I can just say that -1 actually puts the a squared b4 into the denominator. I can expand these brackets out. There's lots of different things I could do. Now this is just one possible way. You may do this completely differently. Here I don't like negative powers, so divide really means multiply. That really means divide, so I'm just going to put it in the denominator. Okay, so here I can group some things together. I end up with a to the power 4, b to the power -8. Well, that -8, this is a divide, so that becomes the same on the right side as I have on the left side. And again, this is just one possible way we could have done it. I could have applied this divide into the powers here as my first step, and that would ultimately give me the same solution. So we talked about this before when we have exponents that are rational numbers. What this means is this numerator means the power, the denominator means the root. So when I write this, I can write this as the cube root of 27 and power 5. Okay, well, the cube root of 27 works out to be 3. 3 to the power 5, we can just leave it as exponent, but we can also put this into the numerical form. This is 243 when we work it all out. So if I were to write this as an exponent and calculate, okay, well, what I know is that exponents and roots are opposites of each other. So if I have a fifth root and power 5, essentially they cancel each other out. We just have the 32 here. Here we have rational exponents and negative exponents. We just have to be a little bit careful when we're applying this. And I can do this many different ways. But when I apply this exponent here, well, this is a power, that's a power, they go together. So I have power 2 to the power 2, it's power 4, and nothing changes with the root here. So same thing here, I can do power to power here. Really, this is the power rule, we're just going to multiply those powers. That means I multiply the numerator and keep the divide in the denominator. So here I'm going to end up with a negative power. This just all means it's going to be divide. I could put it in a fraction, but I'm just going to leave it as a negative exponent. And what I'm going to do here is just I'm going to combine these exponents. So a to the 4/3 plus a to the, I have dividing by 5/3. Really I have an extra 1/3 divide. Here when I put these together, I need a common denominator, so this becomes -16 thirds minus, so -16 over 6 minus 1 over 6. Now I'm applying fraction rules in here, so this is another way I can do it. Here, when I simplify this out, I end up with, well, the roots don't change, the denominators doesn't change when I add fractions. I end up with -17 over 6. Okay, so there's lots of ways, perspectives we can take on this, We can keep track of the roots and powers. We can think of these as rational numbers that we're adding and subtracting in the exponent. Okay, so this would end up being my final answer. I could put this in to positive exponents and roots. That's a cube root. This is a sixth root and power 17. Okay, and the negative just means it goes into the denominator.